Good morning, all. So this is the last week of tutorial sessions. My name is Nishant, and this tutorial covers weak nonlinearity. And welcome to week 12. Right? So, first things first, I want to teach you guys the basics of current injection method. The method is quite simple. Generally, nonlinear circuits are very difficult to handle because it involves finding out the solutions to nonlinear differential equations, which definitely cannot be done by hand, right? So, assuming weak being the keyword, nonlinearity, which is an assumption again, and for most of the cases, the assumption does hold true because if you want linear circuits to be working in practice, you hope the circuit has weak nonlinearity, right? So let us understand how weak nonlinearity works. So you have a circuit. Let's say you have some input, you have a resistance, you have a capacitance, and let's say some element in your circuit was nonlinear. Or why take this example, right? Let's take a box, okay? And there are resistors, capacitors, and a bunch of other MOSFETs, and a bunch of other nonlinear elements, right? So how will this work? You can go and write node equations for each KCL and KBL node, and then solve nonlinear differential equations, right? But unlike the case, what we basically have to do, if you assume weak nonlinearity, is assume, first step is assume the entire circuit is linear. Okay. Now, once you assume that, you find all the node equations. You find basically all the output voltages. And call it VO1. For example, as discussed in class, you basically take an RC filter. You have a certain input and you get a certain output. Assume that each of these elements are linear and find VO1. Okay. Second step is you basically connect input to 0. And let's assume that the resistor is nonlinear and the current through the resistor should basically be R into V, G into V across it, right? Ohm's law. But unfortunately, the resistor is nonlinear and you have all these nonlinear elements whose effect you are trying to find. Okay, to find because of this output current through the resistor, you expect obviously a linear term, a second harmonic, a third harmonic, and blah blah blah, right? Provided a pure sine wave into the chip, right? Provided a pure sine wave to the filter. So basically, hence, you assume in step 1, you assume G2 and G3 is 0 and find VO1. Now, when you find, once you have VO1 and Vin, to find VO2, which is the second harmonic, or say output due to second order nonlinearity, which is this fellow over here. What you do is you inject a current G2 into VO1 minus V in whole square, okay, and find out V into and again your notice should be not this, okay. This is because VO1 and V in, this is a constant current source. Constant current source, but this circuit is actually the solution to the circuit comes from a linear differential equation. Okay, and what is the third order nonlinearity? Third order nonlinearity is basically, let's say, what I mean to say is you want to find out the output for VO3. What happens is basically G2 into VO1 minus Vi whole into VO2 plus G3 into VO1 minus Vi whole cube, right? This is how you find out VO3. Again, I kindly observe that both these guys are known, and hence again the solution to this equation comes from a linear differential equation. Beautiful. Now that we have this background, let us okay. So the next step in our what is what is the next obvious step is to explain to you guys that generally second order nonlinearity doesn't exist due to the use of fully differential circuits, right? So we in practice we mostly only find HD3, okay. We want what is the output of a linear equation, solution to linear equation, and then find HD3. Okay, these are the two agendas that we should hold whenever we solve nonlinear circuits. Okay, so what does that mean? G2 is 0 in our previous example, and hence to find the linear equation, what should you do? Assume the circuit is linear, provide an input voltage, check what is the output voltage. The second, this is the step 1. Okay, step 2 is short the input to ground, provide a current G3 into VO1 minus Vi whole cube and find what is VO3, and final Vout will be VO1 plus VO3, right? As simple as that. Beautiful. Now, we have all the background that we need to, okay, mainly this analysis is used to analyze op-amp nonlinearity circuits, okay. What does that mean? You have a nonlinear circuit. Mostly in real implementations, all the op-amps are non-linear. Generally, all resistors are, in practical sense, linear. You can call it linear, but all uh, active elements like transistors and other blocks are mainly non-linear elements. Okay, so our attention should always be on analyzing the op-amps. Try to understand the op-amps non-linearity as best as possible. Okay. Now, let us say this is a simple non-inverting amplifier. Okay. Now, if I have V in here, and this is ground, this is V out. Okay. Let's say I model the op amp as a voltage controlled current source. V in, not V in, V, let's call this Vx, and ground. This fellow will be Gm into Vx. Right? First, and in fact, this this op amp I'm saying is a non-linear element. Like basically it has, let's say this potential was Vx, the output current, right, will be Gm times Vx plus Gm3 times Vx cube. Hello?
Hello, sir.
Do you have any doubts?
Yes, sir. Sir,
related to the course?
Related to the course only, sir.
Okay. Ask away.
Yes, sir. Related to the course only, sir, not while finding that weak non-linearity term, sir, what are the benefits we can find it, sir, in the application part, if you want to mention?
That's what I was teaching actually. Look, in reality, all the MOSFET-based op amps are only non-linear elements, okay? We want to gauge, in reality, what we have to decide is, if you model this op amp as a VCCS, you want to understand what is the GM that you have to choose. And the choice of GM by hand, okay, by hand calculation, you can, for a given GM3, what is the GM that you have to choose so that your non-linearity is less than a certain amount. You didn't understand.
Already started recording, sir, previous thing.
Sorry?
Sir, previous, what you started, that one?
Yeah, I was recording.
Yes, sir, yes, sir. Continue, sir. Yeah.
Okay, do you have any other questions?
No, sir, that actually that non-linearity term only, sir.
See, Talpasai, when you want to design an op amp, right? You have to decide the GM of the op amp. Okay, given some GM3. Okay. Now, and we hand calculate this first. How do we hand calculate this? Basically, for a given GM3, if GM is more and more, the non-linearity is less and less. We'll have some non-linearity specifications. Through that, we choose GM. Okay.
So while calculating this and all, that non-linear term will be, we make it system is linear, sir.
Basically, you want a system as linear as possible.
Yes, sir. That is our requirement. With the linear, while implementing these things, we can get any application parts, sir, in terms of an application while implementing this. Making linear means it would be system will be stable like that. Any more thing?
I'm not understanding your question.
Yes, sir. Everyone want a system to be linear only, sir. If it is non-linear, there will be no control over it, right? We make it a system as linear only.
Yeah, basically you'll have some non-linearity specifications. Okay, to match those non-linearity specifications, you have to choose a certain GM. the choice of this GM is what we will find with weak nonlinearity. With current injection method. Okay. Anyway, listen on if you have any questions.
Yes, sir. Continue, sir. Continue, sir.
Okay. Now someone comes and tells you that Dalpasai, what is this circuit that I have written?
Inverting amplifier, sir.
It's an inverting amplifier, right?
Yes.
Let's say this op amp is non-linear and I'm modeling it like this. GM Vx. What I mean to say is, let's say this is Vx, okay? So the output is GMVX plus GM3VX cube. Okay? Fine.
Feedback resistance.
Sorry?
Yes, sir.
Okay.
I think, yeah.
And now, what is the first step to analyze the circuit? Assume the entire circuit is linear.
Making GM3 S0.
Yes, make GM3 0. This is the step 1. Okay. So how does the circuit look? It looks something like this.
GM3VX and a feedback
GMVX, ground, feedback resistance, sorry.
RF, R1.
RF, R, V in, V out. Right? Can you tell me what is V out by V in?
Yeah, minus R1 by RF, sir.
No, this is not, GM is not infinite.
Okay. Yeah, fine. Yeah, GM is not infinite. Yeah, V out first we need to find out V out minus Vx. Current.
Okay, first before writing KCL KVL equations, what do you expect? As GM tends to infinity, what becomes V out by V in becomes what?
Minus RF by R1, sir. That is ideal.
Okay. As GM tends to infinity. This is the first step. Step 0. What to expect? Okay. Now let us write KCL KVL equations. Can you help me? V in minus Vx by Ri equal to Vx minus
by RF.
This is equation 1, right?
Yes, sir.
What is equation 2? V in minus Vx by Ri is equal to Vm Vx. Okay. Shall I actually teach you another very interesting way? Let's say GM is large enough. Okay. Let's say GM is large enough. Okay. If op amp was ideal, what would have been this voltage? Minus RF by Ri into V in, correct?
Yes, sir.
And what is this current? V in by?
V in by Vx by,
Vx is 0, right? I mean, if I assume ideal.
Same current will flow, sir. Correct.
Okay. So, this current is V in by Ri. Okay. This current is V in by Ri, correct?
Yes, sir. Yes, sir.
That has to flow through the op amp only.
Yes, sir. That is in series, no, sir. Vn plus, that should be same.
So, GM Vx should be V in by Ri, correct?
Yes, sir.
So, what is Vx? Approximately, it is V in by GM Ri.
Yes, sir. Perfect.
Okay. So, Vx is approximately V in Ri. So, we found out V out is approximately what now?
V out, V out would be...
I mean, just put this here. So, what does it become? V in minus V in by GM Ri is the input current. Voltage, right? Ri equal to, okay, basically I'm asking you to write KCL at this point. Okay, what happens? V in minus Vx by Ri equal to Vx minus V out by Rf, right?
Yes,
so what is Vx?
Vx value, yeah, Vn minus Vn by, yeah, we can take a
Okay, so basically it is you take V in common 1 minus 1 by GMRI equal to okay. And we'll have to let's write it cleanly only, okay, for others' perspective. What happens? V in minus Vx by Ri equal to Vx minus V out by Rf, correct?
Yes, sir.
So V in by Ri plus V out by Rf is equal to
Yeah, Vx we can take common, sir. 1 by Ra plus 1 by, yeah.
Ri plus Rf by Ri
Ra. Yeah.
into Vx. What is Vx? V in by GMRI, correct?
Yes, sir.
No,
Vn now.
what happens? V in by Ri minus
Vn by Gm by Ri.
V in by GMRI into 1 by Ri parallel Rf
Yes, sir.
equal to V out by Rf, correct?
Yes, sir. Vn we have to take a common.
So V in you take common.
1 by Ri.
V out by Vi is approximately minus Rf by Ri into 1 minus 1 by Gm Ri parallel Rf, correct?
Yes, sir. Perfect, sir.
Did I do anything wrong?
No, sir.
No. This is divided by, right? Not
RF will become up on, yeah, perfect. No, sir.
no. Oh, no. This into only, right?
Yeah, into only, sir.
Perfect. Thank you, man. So basically, V out, VO1 we know no. VO1 is minus Rf by Ri into some small factor, K. Right? Some factor alpha, which alpha is very, very close to 1, right?
Yes, sir.
If alpha has to be close to 1, what does that mean? Gm into Ri parallel Rf should be greater than 1, implies Gm should be greater than 1 by Ri parallel Rf, correct? So you got one condition for Gm. Did you understand? If
Yes, sir.
ideally I want V out by Vi as Rf by Ri, but I have some factor alpha. If alpha has to tend to 1, this factor should be as large as possible.
Yeah, the Dm should be, should be much greater than Ra parallel, yeah.
Gm should be much greater than 1 by Rf parallel Ri. Okay? Now, let us understand step 2. What is step 2? You connect input to 0, right?
Yes, sir. We need to connect the input to 0 and we have to inject a current.
This is GMVX. Okay. This is RF, RI. We have to inject a current GM3 VX cube, right?
Yes, sir.
And find out VO3. This will be VO3. Correct?
Yes, sir.
Beautiful. Just a second. Let us see what is the answer. So let us copy over the circuit. GM3. Okay. So can we write KCL here?
Yes, sir. We can write, sir.
VO3 minus VX by RF.
Yes, sir.
Equal to GM3
VX.
Oh, no. Just a second. Plus GM VX equal to GM3 VX cube. Correct?
Yes, sir.
And what is the KCL at this point?
At
VO3 equal to, just a second. Vx equal to VO3 into R1 Ri by Rf plus Ri, correct?
Yes, sir. Division, current division.
Voltage division, you mean? Okay. So basically, VO3 by Rf plus Gm into VO3 into Ri by Rf plus Ri. Okay. No. Let's push all Vx to one side and do it. Okay. VO3
VO3 by RF, and we can take a common Vx here.
Vx by Rf minus Gm Vx
plus Gm3
plus Gm3 Vx cube. Correct?
Yes, sir.
Awesome. So VO3 by Rf equal
1 by Rf minus Gm3 we can take common, sir.
Minus Gm plus Gm3. Correct?
Gm3 Vx square will come out, sir.
Sorry. Yeah, thank you, man. Vx square will come out. Correct?
Yes, sir.
Now, what was Vx from earlier discussion?
V03 by Ri plus Rf plus Ri.
No, what was Vx?
Yeah,
Vx was V in by Gm Ri, right? Correct?
Yes.
Into 1 by Rf. Okay, we'll neglect 1 by Rf when compared to Gm, okay? Because we know Gm has to be greater than Rf parallel Ri, correct?
Yes, sir. 1 by Rf, yes.
So this is neglect. Okay. Then we will have Gm3 into V in by Gm Ri whole square minus Gm, correct?
Yes, sir.
V in by Ri.
Yeah, the Gm3 by Gm and Gm by Gm will get cancelled, sir. That would be minus 1.
Plus Gm3 into V in cube by Gm Ri whole cube, correct?
Yes, sir.
So VO3,
RF, RF it will go that, sir.
VO3 will be minus Rf by Ri into Vi. Is that correct?
Yes, sir. Plus Gm3 into V0, VO3 whole cube by
3 into V in by Gm Ri whole cube, correct?
Yes, sir.
There seems to be something wrong, man, because see, V out is VO1 plus VO3, right?
Yes, sir.
We know VO1 now. VO3 can't have this term.
Okay.
We have done a mistake somewhere. That's what it means. VO3 minus Vx by Rf. Vx equal to Vx. Now, do you find any mistake?
No, So that their current equation might be their KCL, sir. P03 leaving is GM3VX. Yeah, correct only, sir. KCL is also correct. Leaving and entering. We'll go step by step, sir. We'll get understand. KCL is VX.
This equation is correct. This
So-
equation is also correct.
Yeah, sir. That is perfect.
Oh, okay. I know. Sorry. I know what mistake I did. Okay. This is VX1, right? I mean, during initial analysis, VX1. This is not this VX. Did you
Yes, sir.
understand?
Yes, sir. You substituted.
Okay. Yeah. Everywhere I substituted, which is a mistake, right? Okay. So let us rewrite this. Okay. So VO3 by RF. Let's neglect here only. Okay. Is equal to Vx by Rf minus GmVx plus GM3 Vx1 whole cube. Correct?
Yes, sir.
Okay. Let's neglect this. Let's draw it in neglect. Okay. VO3 by RF equal to minus GmVx, where Vx is VO3 into Ri by Rf plus Ri. Correct?
Yes, sir.
Plus GM3 into Vx1 cube. Right? So VO3 by Rf plus GmRi by Rf plus Ri is equal to GM3 Vx1 cube. Correct?
Yes, sir.
Now this is VO3. So can we neglect anything? VO3 into
VO3 we can take common.
Ri plus Ri plus 1 by Rf.
GM3.
Okay, we can neglect this, right?
Yes, sir.
Neglect this also.
Yeah, GM3 into, that's fine, sir.
GM3 into Vx1 cube. So VO3 is basically GM3 by GM into
Ri.
plus Rf by Ri, right?
Yes, sir.
Into Vx1 cube. Correct?
Yes, sir. Perfect.
Okay, so VO3 is what? GM3 by GM into some factor K into what is Vx1? V in by GM Ri, right?
RF plus Ri, sir.
This is Vx1 is V in by GM Ri, correct? Did you understand? Vx1 is V in by GM Ri.
Yes, sir. Correct.
So VO3 is basically GM3 by GM power 4 into GM3 into GM power 4 into I can write it as separately only, I think. GM into 1 by GM Ri whole cube into 1 by K into V in whole cube. Correct?
Yes, sir.
Now, so VO1 is what? Minus Rf by Ri into V in plus GM3 by GM into 1 by GMRI whole cube into 1 by K into V in whole cube. Correct?
Yes,
Let's
sir.
say GM3 is this dimensions correct?
Dimensions. Yeah, GM.
Check. Does this have any dimensions?
GM3. Yes, sir. GM is
GMRI doesn't have any dimensions, right? K also doesn't have any dimension.
Yes, sir. GM3,
Okay.
GM3 will also get cancelled. Sorry, sir.
No, GM3. What is GM3 is this? Oh God,
Simon
current.
says.
Just a second. My power is. I lost power. I'll get back to you. Okay.
Yes.
I'll log in again.
Kitu, Kitu. गुड इवनिंग शांति सर. हाँ सर. हाँ सर. हाँ. हाँ सर. हाँ. Seamless. Sir, automation I had told last time only. I mean, हाँ sir. Understood sir. हाँ. Understood sir. Understood sir. Hmm. Understood sir. हाँ sir. Under that I have told sir. Invisible research. Told sir. Told sir. हाँ. Done sir. Done sir. If I could remove. No sir. Understood. Understood sir. Hmm. One graph. हाँ. Fair enough sir. Understood sir. Understood sir. Presentation was okay sir. No, no, sir. Only presentation. Only presentation I sent you, sir. No, no, you respond. on if you had any other comments that you remember, sir. Huh. Understood, sir. Understood, sir. Fair enough, sir. Huh, sir. Correct, sir. Understood, sir. Huh, sir. Oh, understood, understood. Understood, sir. Fair enough, sir. You can tell. Fair enough, sir. Got it. Awesome, sir. No, that was satisfactory. That's all. They didn't tell anything else. Huh, sir. Okay, sir. Thanks a lot, sir.
Hello, Talpasa, you're still there?
Yes, sir.
Sorry, my professor had given me a call. I had to talk to him.
Yes,
Anyway,
sir.
so if I
Shanti
give,
Pons.
yes, if I give 100 millivolt input, okay, not 100 millivolt is too small. Let's say 600 millivolt input, and RF by RI is let's say 2. Okay. Now, shall we write V out? What is V out? V out will be minus 1.2 sine omega t, right? Plus, let's say GM, I want HD3 of 60 dB, right? Let's give this 500 millivolt then. Okay. So this will be minus 1 sine omega t, correct? Correct, right? If I give a 500 millivolt sine and RF by RI is 2.
Yes, sir. Yes.
Let's say GM3 is 1 milli ampere per volt cube. Okay. 1 milli by. So if I want 60 dB of HD3, what should this term be?
No idea, sir. Actually.
What is 60 dB in? I mean, this should be very intuitive, man. 60 dB is 1 milli, right? Basically, 20 into log of 10 power minus 3 is 60 dB, right?
Yeah, sir. But according to the calculation, we have to make it now.
Yeah. 1 minute. We will write it, but that is 1 milli. That is, you agree, right?
Mm-hmm.
Okay. Coming back. So, this term has to be 1 milli sine wave, correct?
Yes, sir. 1 milli sine wave. According to that, we have to
Find GM, correct?
Yes, sir. GM and K, VN we can make.
No, K is fixed. That is 1 plus RF by RI.
Yeah, RF. Yeah. We have to make that GM RI also. RI we can't change, no, sir.
RI is 1K, let's say.
Oh, RI is also already fixed, no, sir.
RI is given in the problem. Okay. Now I want GM value. Okay.
Mm.
So 0.1 sine omega t. 1 milli into sine omega t, sine cube omega t equal to GM3 I know, right? It's 1 milli by GM into 1 by GM Ri, where Ri is known, whole cube into 1 by 3 into 0.5 sine omega t, right? Whole cube. Did you understand what I did or no?
Actually, without you're making calculations.
So if this is 1 and this is 1 milli, HT3 will be 60 dB, correct?
Yes, sir. 1 millisecond. Yes, sir.
So I am calculating GM. GM3 is known, Ri is known, K is known. I am calculating GM such that I get 1 milli sine wave. Just a second. Just a second.
Yes.
Nothing. Anyway. So I want 1 milli sine cube omega t, right?
Yes, sir. 1 millisecond omega t is the term we needed. We need to calculate according to that GM. We have rest of the values, that GM3 values, that the GM Ri will be, sir, GM R cube. Yeah,
just a second. 1 minute. Okay. I think I'm confusing you. Okay. Let us write it out. Okay. What is minus RF by Ri? It's minus 2, right?
Yes, sir. That is
into
K.
0.5 sine omega t is the input, correct? Plus some factor, okay? Let's call this K3, okay? Into 0.5 sine omega t, right? This is V, right?
Yes, sir.
So let us continue this line of thought. Okay, this is minus 1 sine omega t plus K3 into 0.5 whole cube into sine cube omega t, correct?
Yes, sir. Sine cube omega t we can write like this, sir.
How can you write?
Yeah, 3 by 4 sine omega t minus 1 by 4 sine 3 omega t.
1 by 4 sine 3 omega t, right?
Yes, sir.
Is this correct?
Yes, sir. Perfect.
Okay. I will neglect this, okay? Because it goes with the input, correct? K3 into 0.5 whole cube by 4 into sine 3 omega t, correct?
Yes, sir.
This is with the 0 dB. I want this to be 60 dB down. It should be minus 60 dB. Your understanding?
Yes, sir. Yes, sir.
Okay, beautiful. No. If this is 0 dB, I want this to be at 1 milli sine 3 omega t, correct?
Yes, sir.
So K3 into 0.5 whole cube by 4 is 1 milli, correct?
Yes, sir.
What is K3?
K3
is this fellow.
Yes, sir. GM3 by G. GM.
Copy. Paste. Equal to 4 milli by 0.5 whole cube, correct?
Yes, sir. 0.5 whole cube. Yeah, I can make it. 0.25, sir. 0.125, sir.
No, I can just bring this up, right? Into 8 I can do, right?
Yes, sir.
Okay. Now, GM3 is 1 milli by GM is unknown by GM3 into 1K whole cube into 1 by 3 equal to 4 milli into 8, correct?
Yes, sir.
Milli cancels. Right?
GM power 4.
1 by GM power 4 equal to 8 into,
8 into 3, sir. Correct.
32 into 3 into 1 kilo whole cube, correct? Now what is GM4? GM and then 1 by 32 into 3 into 1K whole cube power 4.
Actually, the 3 will come. Yeah, sir.
Correct, no?
Yeah, sir. Perfect, sir.
Or did I make any mistake? So GM is basically 32 into 3 power minus 1 by 4 into 1k power 3 by 4, correct? Minus 3 by 4.
Yes, sir.
Okay, let's calculate this, okay? 32 into 3 power 96 power minus
It is 11. Sir, that 32 into 3 is 3.130, sir. Correct, sir.
Sorry?
That 32 into 3 whole power minus 1 by 4 results.
Just a second.
Yeah, 0.319.
I'm getting final answer as 0.74 millisiemens.
Okay, sir.
Can you check if it is correct?
Definitely, sir. It will be correct.
I can also do mistakes, man. I think I made a mistake as expected.
Sir, that 1K is 0.7177, sir.
This I think will be 1.8 millisiemens if I'm not wrong.
Okay, sir. Okay, sir.
Can you check?
Yeah, sir. Sure. 10 seconds, sir. Check, sir. 10 seconds. 32 into 3. Yeah.
Yeah, I'm getting 1.8 millisiemens.
Bars. Yeah, okay, sir.
Fair enough?
Yes, sir.
Okay, we'll verify this in MATLAB. Okay? I mean, in cadence, right? Okay. Now,
Dude, my internet went again, man. I'll be back, okay?
dude, can you still hear me?
Hello?
Yes, sir.
Hello?
Yes, sir. Yes, sir.
Okay. I lost power, so I'm trying again.
Okay, sir. Sir, we can do one thing, sir. Yes.
You can't even screen my screen. Just a second. Talpasai, just one thing, man. Can you verify? Okay, I'll upload another video verifying this. Okay, my internet is really bad, so I can't do much.
Yes, sir. Sir, you will off, sir.
Sorry.
You can end the class, sir.
Yeah, we can end the class. I will
Sir,
upload another video. I'll append to this video another time, and then we'll get back.
yeah, sure, sir. Sir, 1 minute, sir. Could you please can you add any 1 point, sir? I will put my abstract, sir. So only it will be at 10 lines only, sir.
Okay, you share the. Just a second. Let me stop recording. Okay.
Yes, sir.
Yeah, okay. Share your
Screen.
Can I post it, sir, in text format, in message?
No, just share your screen. No, if you can.
Okay, sir.
Yeah, I can see your screen.
Yes, sir. Sir, this is the sir. It will start from here, sir.
Amplifier specifically on the saturation, understanding importance of in terms of okay, I mean, the English is bad. The story is not straight. Can you do one thing? Just on a note paper, just tell yourself what you want to tell to the crowd, and then write statements and correct the English. This is all over the place. It does.
Yes.
What story do you want to do?
Yeah, sir. Actually, I would like to implement the common source is there, no, sir. While taking as common source amplifier, while writing the current equations, while we including that one more AC source, how that current equations will change, that harmonic terms will come, no, sir, in current equation.
Yeah. You can do that. Yeah. Okay, I mean, no problem. Yeah, so basically, you have to tell that MOSFET has non-linearity, inherent non-linearity. Modeling that is very important.
Okay.
In saturation region, let us understand what is like that. You have to write a coherent story. For now, it doesn't seem like a coherent story to me.
Okay. So how to start, sir?
I mean,
some key points, sir. I will write it, sir.
I think you are not into everything. Okay, let me type.
Only a few points, sir. I'll work on it, sir. I showed my
in circuit design. Non-linearity is
sir, I posted in my message
network effect which causes performance degradation. This effect has to be modeled, especially in the saturation region. Understanding these effects will lead to correct choice correct operating point choices. Lead to correct operating point choices. The theory also the project is to analyze theoretically these effects and prove the same simulation. Assuming the called analyze theoretically. Analyze these effects. This theoretically, assuming weak nonlinearity. And to prove the same simulation results. Finally, we will some circuit yes to reduce okay. Have given you a basic structure. You play around with it and clean up the English and yeah. So basically,
Yes, sir. Sure, sir. Thank you, sir.
okay. Okay, man. Anything else?
Sir, 1 minute, sir. Just saving it, sir. Your text.
Okay, I'll have to go now, man. Hello, bye.
Okay, sir.